In this section, we'll look at functions of multiple random variables. And functions, again, are just some g of x or g of y that we looked at previously for random variables. But let's look at functions now when we have multiple random variables in play. So assume that we have two random variables and that those random variables have a probability mass function associated with them. Again, kind of the premise for everything we've talked about in this lecture so far. We have the random variable x, and that has a probability mass function of p of x, and the random variable y with a probability mass function p of y. Now, in this case, we're going to also assume that we have a random variable z, and that we can express z as a function of x and y, some g of x and y. Now, the probability mass function of the random variable z, we would say is, well, the probability mass function of z, but that is equal to the probability that the random variable z, or the function of the random variables z, is equal to little z. Now, remember that the function of a random variable is still a random variable. And so we can say that this is also just the probability that the g of x and y function that we've said that z is equal to little z. So we're just substituting in that function. Now, another way to express this and to simplify this is to say that this is the sum over all possible pairs of x and y where that function of x and y is equal to little z multiplied by the PMF of x and y. So we're going to take the summation over all values where we're equal to little z, where the function of x and y is equal to the value that we're interested in, and multiply that by the PMF of x and y. Again, the PMF is just the probability that's occurred. And in this case, we're looking at all the possible places where that probability's occurred, and we're going to sum those up. Now, this leads to an extended version of the expected value rule. And the expected value rule in this case becomes that the expected value of a function of a random variable of g of x and y, we can sum over all possible values of x and all possible values of y. And we, again, just substitute in this function g of x and y. And we multiply by the PMF of the random variables x and y, again, the joint PMF in this case of x and y. And this should follow pretty easily from the expected value rule and the joint PMFs that we've looked at previously. But it is important. This is going to be an equation that you will probably want to have in your toolbox as we progress through the course. So let's assume that we have a joint PMF of two random variables x and y. And let's let a random variable z be equal to the sum of those random variables x and y. So a question we might ask is, what is the expected value of z? Well, as you might recall, I said we have a joint PMF of x and y, so let's create that real quick. And let's assume that this is our joint PMF of the random variables x and y. Now, what is the expected value of z? Well, we said that it's the sum over all x and over all y of the function g of x and y multiplied by the PMF of x and y. And in this case, it's a joint PMF, so we have a lot of variables that are equal to 0 for a PMF, so we can ignore those because 0 multiplied by anything is just 0. And then we have three terms here that we're really interested in. And that is this 1/2, 1/4, and 1/4 that are the only three intersections, if you will, of the joint PMF where there's a non-zero PMF. So with that, if we look at each of those, the joint PMF, the expected value of this joint PMF where z is equal to x and y, is just going to be the value of z, this g of x and y for each intersection where the PMF is non-zero, multiplied by the probability of that given intersection. Putting some numbers to this, let's look at these intersections one at a time and we'll sum over them. So the first one that we'll look at, we'll say is this 1/2. And so we would say that this is equal to the sum of x and y, of little x and little y in this case. So that would be 4 plus 2, that intersection value. So we would have 4 plus 2. And then we would multiply that by the probability mass function of that intersection. So this would be multiplied by 1/2. Then the next term that we would look at is this 1/4 here. And you can look at these in any order. It's a summation. We're just going to pick this order. And we can say that we would add that. Again, we're summing over x and y. So at this point, we have a 3 and a 3 for our values of x and y. So we would add 3 plus 3. And then we would multiply that by the probability of that intersection, which is 1/4. So we would take that 3 plus 3 and multiply by 1/4. Then finally, we're going to add this last term, this 1/4 up here at 4 and 4 as our xy coordinates. So we would say that now we're going to add 4 plus 4. And again, multiply that by the probability of that intersection, which is 1/4. Now, when we sum all of these together, we find that this is equal to 6.5. And you can also express that in terms of fourths or halves or whatever you'd like, but ultimately this is 3, this is 1.5, and this is 2. And so when you add all those together, you get 6.5, and so you can say that the expected value of this function z, which is a function of x and y, is equal to 6.5. Now another way to say that is that the function of the sum of x and y is equal to 6.5.